Have you ever just stopped and wondered what's holding everything together? I mean, from the water you drink to the very screen you're looking at, our entire world is built by these invisible forces that connect tiny, tiny atoms. Well, today we're going to pull back the curtain and explore the fundamental glue of our universe, chemical bonding. This idea is not new at all. Way back, over 1,000 years ago, the chemist Jabir bin Hayyan noticed that elements seem to have, well, preferences. They attract some elements and push others away. It's a fantastic insight because it frames atoms not as these boring little specks, but as active players in a huge cosmic dance of attraction and repulsion. And yeah, that leads us to the big question here, right? An atom doesn't have a brain or feelings, so what could it possibly mean for it to want something? What's the driving force behind all this behavior? Well, it turns out the answer is a universal quest for one single thing: stability. So, let's dig into what this desire for stability really means. It's not a conscious thought, of course. It's a fundamental drive, hardwired into the laws of physics, this deep, powerful need to reach a state of perfect balance. And this, right here, is the golden rule of that stability. It's called the octet rule. So think of an atom as having these layers or shells of electrons. For most of them, the ultimate goal, the end game, is to get that outermost shell perfectly filled with 8 electrons. A full shell is the most stable, most content an atom can be. And that's it. That's the entire motivation for all of this bonding. What's really fascinating is that there's this one group of elements on the periodic table, the noble gases, that are basically born perfect. They already have a full outer shell of 8 electrons, naturally. This makes them super stable and frankly kind of lazy. They don't react with much. All the other elements are essentially looking over at them and trying to achieve that same perfect setup. We call it noble gas envy, which is a fun way to think about this atomic ambition. So how do they actually do it? How do they get that perfect outer shell? Well, let's move on to strategy number 1. This is the most straightforward way to do it. One atom just gives an electron away and another one takes it. Simple, direct, and incredibly powerful. This whole process creates what we call an ionic bond. And the key word you have to remember here is transfer. This isn't a loan, it's a permanent giveaway. This transfer creates ions, which are just atoms with a positive or a negative charge. And, as we all know, opposites attract. That powerful magnetic pole, that is the bond. The absolute classic example is table salt, sodium chloride. Look at this. Sodium has one lonely electron in its outer shell. It is desperate to get rid of it to become stable. Meanwhile, chlorine over here has 7, and it just needs one more to hit that magic number of 8. So it's a perfect match. Sodium gives its electron to chlorine. And boom. Sodium is now a positive ion, chlorine is a negative ion, and that powerful attraction just snaps them together. And this right here perfectly illustrates the incredible magic of chemistry. Think about it. Pure sodium is a metal so reactive it literally explodes if you drop it in water. And pure chlorine, that's a poisonous gas. But you let them form an ionic bond, and they create sodium chloride, table salt, something our bodies absolutely need to function. It's an amazing transformation. Okay, but what happens if neither atom wants to give up an electron? What if both atoms actually need to gain electrons to get stable? Well, that leads us to the second major strategy, which is less like a transaction and a lot more like a partnership. This is a covalent bond, and the key word this time is share. Instead of one atom giving an electron to another, 2 atoms decide to hold on to electrons together, in common. That way, both atoms get to count those shared electrons toward their magic number of 8. It's a totally cooperative solution to the stability problem. So just to make it super clear, here's the difference. Ionic bonds are all about the transfer of electrons, usually between a metal and a nonmetal, which creates those charged ions. Covalent bonds, on the other hand, are about sharing electrons, usually between 2 nonmetals, which creates a neutral molecule. Now, within this idea of sharing, there's another really cool layer. See, atoms don't have to share just one pair of electrons. They can share 2 pairs or even 3. And here's the kicker. The more pairs they share, the stronger that bond becomes, and the more energy gets locked away inside it. This chart just makes it crystal clear. Take a single oxygen-oxygen bond. It has an energy of about 144 units. But a double bond, like the kind in the oxygen gas we're all breathing right now, bam, it jumps all the way up to 498. And then look at the triple bond in a nitrogen molecule. It's a staggering 945. That is an incredibly tough bond to break, which is why nitrogen gas is so stable. Okay, so we've covered giving, taking, and sharing, but there is one more really unique strategy, and it's used exclusively by metals. It's a kind of extreme community-wide sharing that explains why metals are, well, why they're metallic. The absolute best way to picture this is with something called the sea of electrons model. So in a chunk of metal, every single atom gives up its outer electrons, but not to any one specific atom. Instead, they donate them to this big collective pool that just flows freely around the entire structure. So what you end up with is this fixed grid of positive metal ions, all just sitting in this flowing, mobile sea of negative electrons. The bond itself is the attraction between all those positive ions and that surrounding negative glue. It's what holds the entire piece of metal together in a really strong but still flexible way. And this model? It brilliantly explains the properties of metals that we see every day. Why are they such great conductors of electricity? It's because that sea of electrons is free to move. You apply a voltage, and those electrons just start flowing, creating a current. It really is that simple, and it's all thanks to this special type of bonding. So we've seen the how. We've looked at the three main types of chemical bonds. But now let's talk about the why. Why does any of this actually matter? Well, because these invisible forces, they aren't just some abstract chemistry concept. They are literally the architects of our reality. Just think about this for a second. Every single thought you have, every move you make, is powered by ionic bonds. The salts in your body dissolve into ions, right? Well, the movement of those charged ions across your nerve cells is what creates the electrical impulses that are quite literally the language of your brain and your muscles. And if ionic bonds are the power source, then covalent bonds are the actual building blocks. The sharing of electrons between atoms like carbon, hydrogen, and oxygen is what makes it possible to build the complex, stable molecules that life absolutely depends on. I mean, just look at this list. Water, the very solvent of life, sugars that give us energy, the amino acids that build our proteins, and of course, DNA, the blueprint for our entire existence. Every single one of these is held together by covalent bonds. Without the sharing mechanism, life as we know it would just be impossible. You know, when you take a step back and you see how these simple rules, giving, taking, and sharing electrons, can produce such an incredible diversity of things, from a simple grain of salt to something as complex as a human being, it's truly awe-inspiring. It really points to an elegant, intricate design woven into the very fabric of our universe. The rules of chemical bonding are just one set of these fundamental principles. And it kind of leaves you wondering, doesn't it? What other invisible laws are out there, operating all around us, quietly, and perfectly shaping the world we experience every single day? It's definitely something to think about.